Hello everyone, in this video I'll talk about all four quantum numbers and I will visually explain them, what they actually mean, what they represent. Let's go ahead and get started. The first one, principal quantum number. So what does it tell us? The principal quantum number is represented by n. It tells us the energy level of the electron and its average distance from the nucleus. So we have here the Bohr's model. You have seen this from your Gen Chem, Bohr's model. In the middle we have Nucleus, and then these are orbitals, so they represent by n. So the first orbital is, this is n is equal to 1, and then the second one is n is equal to 2, and then the third one will be n is equal to 3 and 4 and 5 and etc. So these are the orbital, the energy level. So basically the principal quantum number tells us that the energy level of the electrons and its average distance from the nucleus. If we have electron, we have this electron that's running around nucleus in a circular motion, and so each orbital contains maximum 2 electrons, and then etc. So the higher the value of n, the further the electron is on average from the nucleus, and that higher its energy. You can imagine it's much like a Bohr's orbit, as I mentioned, where n is equal to 1 is the first shell, n is equal to 2 is the second, and so on. Each n values defines a main layer or shell that can hold electrons at specific energy. So the principal quantum numbers are fairly easy. So it's just how far they are from the distance from the nucleus. So that one, if this one is 5 centimeter, for example, of course, and that one would be, for example, 10 centimeter. And then the energy level will going high and high. Their energy will start increasing as the number of circle increases, as the number of n increases. So that's what the principal quantum number is. The second quantum number, angular momentum. Angular momentum is determining the shape of the region in space. It's called the orbital, as I just mentioned it. So where the electron is most likely to be found. So now in Bohr's model, electrons moved in a flat circular path, just like I mentioned it in the first principal quantum number. But now in the quantum model, it replaced those with a 3D standing wave around the nucleus, the probability that clouds where the electrons exist. So instead of this 2D, now we have here each orbital is now in 3D. So, and then what exactly the shapes are? The first one is, you see, as not a line now, not just a ring. The first one represent, you can imagine it as a spherical. Call it S orbital. You can imagine it. It's not just a line, but it's a sphere. The second one, the P orbital, that would be a dumbbell shape. Dumbbell shape. So, and this one will be P orbital. The third one would be a clover leaf shape. The fourth one, the F orbital, can be that more complex shape. So the spherical would be kind of circle, but it's more in a 3D spherical shape. The second one, again, it's like a dumbbell shape. So you can draw it like this. Right in the middle, there is a nucleus. So instead of imagining it as a Bohr's model, where just a circular, just a line, or just a ring, now these rings are actually 3D. And what they mention, what they represent the basically the shape of the region, and they represent the probability what is most likely, where the most likely the electrons will be found. Okay, so this is what the angular momentum represents. The third one is magnetic quantum number. The magnetic quantum number, it says the orientation of those orbitals. So once we know the orbital shape, the magnetic quantum number tells us how that shape is oriented in space, which direction it points relative to the three axes. So now I draw this as just a normal shapes on the space, but now they are not just standing like that. Now they are, I'll just draw the line. They stay in a position in X, Y, and Z. Now they have a specific position there. They're not just hanging on the space like that. So for example, the dumbbell, the first one, the S orbital, it doesn't matter because it's a sphere. This doesn't, it only has a one orientation, as sphere looks the same in all direction. The second one, the P orbital, that one has the three different, they stand in three different directions. The first one would be like that, just I draw. The second one will be like that, more horizontal. And then the third one will be actually, it's pointing towards you. So I don't know if I can draw it. So I apologize, but this is how it looks. So it's basically, it's pointing towards you, and that's what you're only seeing this part. So their specific orientation in the orbital and how exactly they stand. So they are not just floating on the space, but now they have a specific the position, the specific orientation. Okay, the fourth quantum numbers, which is also called as a spin quantum number, they represent the spin of the electrons. Now they describe the intrinsic spin of the electron, its internal magnetic orientation. So now within this, each orbitals, now we have electrons. And how those electrons do stay inside those orbitals. That's what spin quantum number says. And so now we know that in the first principal quantum numbers we have those orbitals that exist, and they're kind of moving around. The electrons are within the orbital, and then electrons are spinning around nucleus. And now in angular momentum, now we know that actually they are not a line, a circle as Bohr's model, but now they are more like a 3D shape. And in the magnetic quantum numbers, now we know that they're 3D shape, but they also have a specific orientation. They stay in XYZ direction. They're not just standing, that's just floating on the space. So now the fourth one is the spin quantum number. The spin quantum number is more like, it gives us the electrons position there. So how electrons inside this, it's internal magnetic order. So how this inside this electrons it stands. So it's like a compass, has only two possible values. The property gives electrons their tiny magnetic momentum. In each orbital, two electrons can coexist only if their spins are opposite. So one up and one down. So for example, if we have this orbital, so one electrons, you can say it as a one spin up and then one spin down. So this is what we typically describe it in general chemistry, but it basically how these electrons are positioned within this orbital. Okay, so one might be here and then one might be here, the electrons, and how these electrons are standing. So might be one pointing up and then one pointing down. So the rule is know that the Pauli exclusion principle, it ensures that no two electrons in the same atom have exactly the same four quantum numbers. So which makes sense. In each orbital, only 2 electrons exist. Only 2 electrons in one orbital. So one is spin up and then one is spin down. In that case, so we know that there is no 2 identical electrons, even if in the same shell, in the same orbital. But one will be the electron is pointing up, the one is electron pointing down, and that's what Pauli trying to tell us. So in summary, the first one tells us the principal quantum number, tells us the energy level. The second, angular momentum, tells us the shape of the orbital, and then the third one tells us the orientation of that shape, and then the final one tells us the spin direction of the electron, either up or down, within this each shell, within this each orbital. Apologize.